passed out for you guys your the syllabus sign-in sheet. So at some point, like, fill it out, show your parents the syllabus, have them sign it, bring that back. It's the first homework assignment. You can give it to me physically, or easier, you can put it in your OneNote and submit it digitally. Either is fine. Okay. Plan for today, we're going to look at sections 2, 3, and 4. Not a lot there. Basically, you can put numbers in scientific notation, do some basic exponent rules, like some basic exponent log stuff, exponential log stuff, like the real basic stuff. And that's kind of it for today. The plan will be that next class we'll do like a classwork assignment for some practice, and then the following class will be this first chapter 1 test about what kind of number is this, how to round stuff, scientific notation, exponents, logarithm, real basic. Yes, sir.
Proverbios está ligado no.
No.
Are we not gonna like do that in IB?
Typically not.
Oh, that's it was helpful too. I didn't do it.
I will say that I've also posted the first homework book assignment, which is just the chapter 1 review problems. So I think that's pages 23 to 26, 1 through 20. Again, it should be relatively straightforward. If you hadn't figured it out yet, you probably haven't, because you probably haven't looked at the book, but all the answers to all the problems are in the back, so you can check everything as you go. I would say be cautious, because the person that edited our textbook did an abysmal job. As I think that people change problems and then they never change the corresponding solutions in the back, so there'll be some problems where it's just like, my answer is not even close to what's back here. It's very possible that it's just like, a terrible typo. So be cautious on that. If you're like, I really think I did this right, you very likely could have the correct answer. Some chapters are perfectly fine, and some chapters it's like just a train wreck in the back of the book. So, but there we go. That's what we have. I hope they got fired. Not many. I don't want anything bad, but you did a terrible job. All right. Today, exponent laws. So, these guys are well, we've seen these a lot, right? This is probably since maybe even pre-algebra 1 we've talked about exponent laws. So just as a reminder, an exponential function is something that can be written as the form a times b to the x, where a is non-zero, and then b is positive, not equal to 1. Why does a have to be non-zero? What happened if a was 0? The whole thing's 0. That's a constant function, not exponential. What would happen if b is 1?
It would just be that x doesn't matter.
1 to the x is just 1, so a times 1 is a. That's a constant function, not exponential. What would happen if b was negative? Why don't we allow b to be negative?
Because it goes down instead of up. Because it's an exponential.
If you make a negative, it'll flip it. B being negative, we have a whole different problem. So values that x can have are all real numbers, right? So x could be like a half, a fourth, a sixth, an eighth, right? What is a power of 1/2 the same as? What? Nope. So if you have an exponent of 1/2, that's the same as what? A square root. Can I square root negatives? No. What's a 1/4 power the same as? A fourth root. Can I fourth root negatives? What about a sixth root? Or a 1/6? Same thing, right? You get the idea. This would have discontinuities everywhere. It would be a complete and total train wreck mess. That's why we don't allow B to be negative, right? We want that exponential function to be continuous and not be like riddled with infinitely many discontinuities, which would be like just a mess. Typically that A coefficient we refer to as the initial value of the function, because when x is equal to 0, b to the 0 is 1, unless b is 0. And if so, just the function be equal to a, we call b the base. So every time x goes up by 1, the output goes up by a factor of b. Right? Exponentials are multiplicative is the pattern on the y. And then remember that all exponential functions have a horizontal asymptote at y equals 0, specifically like as x goes to negative infinity, the function should be approaching 0 regardless of whether it's flipped upside down or not, right? Whatever. Yeah, it just order of operations, right? You gotta do the exponent before you multiply. All right, so just a couple of quick examples, like can we plug in values for x and get the correct output to come out? So my function, f of x equals 3 times 2 to the x. If I plug in x equals 2, we get 12, right? We have to do 2 squared first, which is 4, and then times 3 to 12. Should be real simple. What if x is 0? 3, right? 2 to the 0 is 1, and then 3 times 1 is 1. 3 times 1 is 1. You know what I mean. About negative 3. 3/8. 2 to the negative third is 1 over 2 to the third, which is 1 over 8, and then times 3 is 3/8. Right? Again, is this stuff you have to be able to do in your head? No. In this class, calculator is a given throughout. There'd be never any time where we restrict you from using a calculator. You can use your calculator in all parts of your IB exam. Okay, so if you're like, yo, my mental math skills are a little rusty on these things, does it matter? Not really, right? You can get it. You can calculate it if you need to. Although at this level, I hope that many of us are able to grind through these in our head pretty quickly. 1/2. X is 1/2. What do we get? √2, right? Can we do the square root of 2 to get an exact value? We cannot. So typically we'll just write that as 3√2, right? If this was an IB exam, you could also type that in calculator, press enter, and then round it to how many sig figs? 3 is the standard, unless they tell you otherwise, exact or rounded to 3 sig figs. So 3√2 is fine. You know, like 4.2 whatever, I don't know what it comes out to. Square root of 2 is about 1.4, give or take. So, yeah. Negative 3/2. Let's think about this carefully. There's a lot of things going on here, right, to hold in your head. So let's do the negative exponent to make the reciprocal. Then let's do 3/2 as 3 times 1/2, right? So multiplication of the exponent is the same as exponent of an exponent, so we'll call it 2 to the third to the 1/2. Everybody's good there? 2 to the third is 8. 1/2 power is a square root. We can reduce the radical of square root 8 as 2 root 2. Is it okay that I didn't show the arithmetic for reducing the radical of square root 8? We're okay with that? Rationalize the denominator. And we're at 3 root 2 over 4. Yowzer, Mr. Kulak. Man, just arithmetic, you know. You gotta like manipulate your exponent rules effectively. But not big deal. That was as bad as it would possibly get. Done finally. Our basic properties for exponents. These should all be familiar. These are the properties you've probably seen since pre-algebra, realistically, some of these. Do you need to memorize these? No. Should they be memorized, basically, at this point, though? Yeah, the expectation would be that you would be able to use these fluently to simplify a problem without having to look them up, but for example, on this test, they would be there. But I suspect that most of us probably have these things committed. I would say there is one little piece here missing for a couple of these. What little detail is kind of missing from a couple of these? Let's be specific, eh, Mr. Hulick? What would be missing from this statement? We said A, B, M, and N are just real numbers. Is this true for all values of A and M? What value of A does this fail? 0, right? Why 0? 1 over 0 is definitely not equal to 0, right? 0 to the negative m is 0. 1 over 0, n ain't 0, Mr. Kublai, right? We'd make a similar argument here, right? A can't be 0. Similar argument here, B can't be 0. These kind of things, right? The one place where I surprise catch kids, 0 to the 0, not 1. For my 3 calculus students, we'll talk about specifically 0 to the 0 and a couple of other classes of statements that are different than undefined. 0 to the 0 is not undefined, it's a different thing than undefined. It's something worse, it's called indeterminate, where I can write a problem that whose limit a limit goes to 0 over 0 that has any answer I want it to have. Could be 1, could be 2, could be 3, could be 4. What I can make any problem I like that looks like 0 to the 0 or 0 over 0. There's a couple of different classes. There's 6, I think, indeterminate forms. But that's for a different class. That has nothing to do with the rest of you guys. All right. To solve an exponential equation, it's kind of 2 routes I could take for a problem like this. So we'll look at the first route. First thing I'd want to do here is divide by 20, right? We got to get that x by itself, so that thing in the exponent has got to go. So we'll divide both sides by 20, and then I reduced 5 over 20 to 1/4. Now, if I look at the left-hand side of this equation, the base of the exponential is 1/2. If I look at the right-hand side of the equation, I can write 1/4 as an exponential with a base of 1/2. Right? Because 1/4 is 1/2 squared. Will this always be simple to do like this problem? No, not necessarily. This is a special situation. If it was not simple to do this, what would we need to use? A logarithm. Very good. So, since we were able to write these with the same base, if the bases are the same and the two sides are equal, what can we say about the exponents? They have to be equal. So x over 3 has to equal 2. So my answer should just be 6. Is this okay? Typically in this section, any solving problem you'd be asked to do could be done in this kind of fashion, where it should not be difficult to rewrite the two sides to have the same exponent base without using a logarithm. Although if you elected to use a logarithm here, it would not be incorrect. If you're like, I'm just gonna log, just do my logs. I feel good about logs. I remember how to do them. Go ahead and smash the log. If that's what you feel. No worries. And again, pointing out that all these equations like this are checkable. Do you need to check an exponential equation if we're solving? Can we get an extraneous solution for this type of equation? No. No. And the reason you know that is the domain of an exponential function is all real numbers. So even though we take that exponential equation and convert it into a polynomial, when we said x over 3 is equal to 2, the domain for both of those is all real numbers, so we can't run into a extraneous solution. Now, if we have a logarithmic equation, the domain of a logarithmic function is x greater than 0. And if we convert that to a polynomial whose domain is all real numbers, those two domains are different. We can run into an extraneous solution there. If the answer to the polynomial falls in the restricted values of the domain for the original. So that's a situation where you have to check. You don't have to worry about checking for extraneous on an exponential. Any checking you do is just like standard checking. Make sure you got the answer right. That's it for section 3, right? Does that feel okay? I meant section 2. I said 3. All right. This is going to be section 3 and 4 together. Section 3 is just about putting things in and out of scientific notation. Whoa, guys. Are you ready for some SciNot? SCINOT. Scientific notation. Right? Now, here's the inconvenient thing. You know what the IB calls scientific notation? They call it standard form. Right? Yeah, that's something that would be in the direction. I'll use the same vocab and the same notation, the same terminology that the IB is going to use on my tests. Now, we call this scientific notation. IB calls it standard form for a number. Although what they will do whenever they refer to something as standard form, they also say where, A times 10 to the K, where A is between -10 and +10, right? So they tell you the definition of what standard form means, and you should hopefully recognize that as all we're doing is talk about scientific notation here, but worth mentioning, right? Anytime the IB language differs slightly from our normal Americanisms, I like to point that out. Okay, so let's say we have the number 5,120,000. When I convert this into scientific notation, note that I have to turn this first number into something between -10 and +10, right? Everybody remember this? So to do that, I'm going to have to move the decimal point from here to here. So 1, 2, 3, 4, 5, 6 places. That's 6 tens. So that's going to be times 10 to the 6, right? Do you guys remember doing this? I'm hoping this is like a middle school skill here. They probably talked about scientific notation the first time. But I'm sure you've run into it a whole heap of times otherwise in science classes and whatnot. Same thing is true if I have a very small number. So again, I want to take this and turn this first number to something between 0 and 10. So I have to move the decimal point from here to here. So 1, 2, 3 places. Since my number is going from something very small to something bigger, instead of multiplying by 10, we're dividing by 10, which means it's going to be a negative exponent. So we divided basically by 10 3 times, so we're going to have 10 to the -3rd. Everybody's okay? In general, if you're moving the decimal point from left to right, positive exponent from right to left is positive exponent. If you're moving the decimal point from left to right, negative exponent. Right, I think you guys probably remember that, I hope. So if I start off with something in scientific notation, I want to convert it back into a normal number. Always got to move the decimal point to the right because it's a positive value. And then 6 places. So, everybody feel okay there? So we have 2 places for the 1 and the 2, and then 4 zeros after that. Likewise, if it's a small number, this time we're going to move the decimal point to the left. And then since it's -3, it's going to be left 3 places. So 1 place for the 6, and then 2 zeros decimal. Right, everybody feel okay? Can your calculator do all this stuff for you too? If you know how to ask it. Everybody feel okay with scientific notation? I have very little there to do because, guys. If you have trouble doing operations in scientific notation, like 5.2 times 10 to the 3rd plus 7.6 times 10 to the 4th, what can you do? You can just do it on your calculator, right? What's the easiest way to do scientific notation on your calculator? Yeah, that EE button, which I think is second to number 7, I think. If anybody's got their calculator out, confirm that. Sorry, is that where it is? Yeah. So the E key substitutes for times 10, and then you just write the exponent. Right? Is anybody not familiar with that command on their calculator, using that button on their calculator? I'm guessing from science class you guys have done that a bunch of times, right? If you've done chemistry and had to deal with Avogadro's number, I'm sure you've run into that a whole bunch of times. All right, last section in chapter 1. Talk about exponents and logarithms. So we have our basic properties of exponents, right? These are the same ones that you wrote down earlier. Should you bother writing down a second time if you're copying notes? Probably not necessary, right? You just wrote them like 2 slides ago or something. Right? The point of me showing you this is I want to show you the corresponding logarithm properties. So remember, the basic definition of logarithm says if you have the exponential equation b to the y is equal to x, that exponential equation is equivalent to the logarithmic equation, log base b of x is equal to 1. So the base on the exponential becomes the base of the logarithm. The input to the exponential function becomes the output for the logarithmic function, and the output for the exponential function becomes the input to the logarithm, right? Everybody see the switcheroo that's happening? So our super basic properties is log base b of 1 is 0. That's the logarithmic equivalent to b to the 0 is equal to 1. Right? I have the exponential equivalent to it. Log base b of b is 1. That's the same thing as saying b to the 1 is b. And so on and so forth. I'll let you guys kind of read those as I talk a little bit as a higher level concept here. So when we talk about algebra and talk about mathematics, most of us think when we hear the term algebra, you guys probably think solve rings, right? In mathematics outside of high school, algebra is not defined by solve rings. Algebra is about finding structure between sets under a different operation. And then the hope is that you can find some math that takes something from one set with one operation, you can map it to a new set with a new operation, and everything you had in this set, you have an equivalent property in the new set. That's essentially what's happening here between exponential and logarithmic functions, is you have the set exponential is like all real numbers with multiplication. That maps to positive numbers with addition. And the map there is a logarithm, so multiplication turns into addition, and that's kind of what's going on. All the properties kind of follow through. This is what you'd be concerned with if you are, if you plan on being a math major, your capstone, one of your capstone math classes would be like abstract algebra, which is, you'll start talking about these different algebraic structures and why they're important, what you can do with them. Yes, sir?
Yeah,
certainly. Just a couple of quick vocabs. The common logarithm is log base 10. When we write that, we just write it as log with no subscript. Just like, a square root is a radical index 2, but we never write the index 2 there. We just write square root. Everybody's okay with the common logarithm? It's just log base 10, right, as log. This other is the natural logarithm. Remember, that's log base e. Instead of writing log base e, though, we write ln. When I write it, I always write cursive L and cursive n because L looks too much like the number 1 in my penmanship, so I always try to make sure I write my L's cursive so I don't confuse it with the number 1 on my paper, because boy howdy, that's easy to do. Particularly if you're doing like an equation like length times width equals area or something, that L can turn into a 1 real quick if you're not paying attention. So I like cursive L's. Oh, and again, the common log and natural log are buttons on the standard screen of your calculator. There they are right there for this fancy editing on this PowerPoint slide. Right. You guys should all know where these things are. You all did a course in pre-calculus and algebra 2 and should have done these things. So one way you can do this kind of a problem, if I ask you to evaluate log of 100, you should recognize log as log base 10. And then you can use your property or your definition of a logarithm, I should say, to rewrite that as 10 to the x equals 100. And at that point, you should very easily recognize that what power of 10 is 100? 2. Right? 10 squared is 100. Now alternatively, you could think about this as log base 10 of 10 squared, and I know log base cancels exponent base, and I'm left with just 2. That's it's equivalent, like conceptually what you're doing is the same work, it's just presented in a different way. Like you can think about it that way if that's more natural to you. That's the way I tend to think about things. Because I like canceling exponent bases and log bases, that feels natural to me. Yes?
May I go to the bathroom?
Certainly. What about this guy here? Log base of fifth root of 10. I'm sorry, log of fifth root of 10. When I see this, fifth root of 10 is the same thing as what exponent? 1/5, right? So I have log base 10, 10 to the 1/5. Log base cancels exponent base, and I'm left with just 1/5, right? Alternatively, if you want to use the definition of a logarithm, you can go and turn it into an exponential equation. And then using our exponent property for radicals, fifth root is 1/5, and there it is, x equals 1/5. So whatever feels more natural to you, you can do. Again, you guys have had full courses in pre-calculus and algebra 2 and have seen logarithms probably twice at least by now. So like, I'm hoping this stuff is reasonably familiar. That's not hugely important. We don't do a ton with logs in this course. It's just kind of like, it's a basic number operation thing. How about log of 1/1000? So again, when I see this, I see 1/1000. Well, that's 1/10 to the third, which is 10 to the -3. Log base 10 cancels exponent base 10, so this should be -3. Alternatively, you can do this as using the definition of a logarithm. So you do the little switcheroo-ski, and then you'll use your properties of exponents to conclude that -3 should be our result. Either way of approaching it is fine. It's doing the same thing. You're using the same properties, just kind of like conceptually in a different kind of pattern, right? It's whatever, right? You get the right answer is the right answer. Also worth pointing out, like you could type that into your calculator as well, right? Log of 1/1000, and it'll output -3. Also totally doable. 10 to the log base 10 of 6. So again, log base 10 cancels exponent base 10, but similarly, exponent base 10 cancels log base 10, so you're left with just 6. Yep. Right on there, Josh. So again, if you want to, you can do the old switcheroo-ski, and we have log base 10 of x equals exponent, or log base 10 of 6. The log bases are the same and they're equal. The insides have to be equal. So just x is equal to 6. Oh my gosh. You guys remember doing this stuff? I know, right? This is why I don't feel bad about turning around and doing a testing the same week that we introduce these things. Because like,
This is gonna be on the test, right?
nothing we're doing is terribly complicated, right? Yeah, this could be test stuff, but like, it's pretty simple. All right, what about this guy? Log of x is equal to 4. So again, you could think about doing exponent base 10 to both sides to cancel out the logarithm and end up with x to the 4th. It's 10,000. Or you could do our definition of logarithms and switch everything around. Do our little switcheroo-ski, and you're just left with x equals 10 to the 4th, which is again 10,000, right? 1 times 10. No, 10 times 10 to the 3rd. third is just 10 to the third.
Oh, yeah,
Right.
10 times 10 to the third.
Yeah.
Yeah, no, it just takes a second.
Or just 10 to the fourth is the scientific notation version of it.
Some people learn their history.
It would roll, it would be
Alright.
delicious.
How about this guy? Log base 2 of x equals 5.
Some people learn different speeds, Josh. It's okay.
Yeah, so you could just say 2 to the 5th, right? We do exponent base 2 to both sides. Log base 2 cancels with exponent base 2. And we're just left with 2 to the 5th. Or you can do your definition of logarithms to do your old switcherooski. 2 to the 5th is 32. But I think that if you left your answer as 2 to the 5th, like the IB grade would count that as correct. I don't think they would keep it.
What about your test?
I would count as correct. That'd be fine. Unless I ask for this like in scientific notation or something. And it's like, well, it's not scientific notation. You got the right answer, wrong presentation. You know. But if there's no direction given as to like how you need to write your answer, 2 to the 5th, 32, 3.2 times 10 to the first. They're all good. You're right. Mike, remember there's also this thing called the change of base formula for logarithms. Now, is this an important formula for you guys?
Yes. No.
Why not? Because you can just type any change of base formula into your calculator, right? Like you can do log base 2 of 3 on your calculator, just type it and press enter. When I was a student, calculators didn't have logs on them. What you had in the back of the textbook was a table that had like, just a big long list of, natural log of, and then a bunch of integer values, and they had like decimals going across, and you have to like trace over and find. But you have to look the value up off the table. So if I wanted to do log base 2 of 3, I had to look up log base 2 and look up log base 3 and do the decimals in my calculator with the division. That's what it looked like. Now, you guys don't need to do that, right? You just use the log base button on your calculator and type it in exactly as it looks and press enter, and the calculator handles the whole thing for you. So this formula is a whole lot less useful. I would use this anytime I had a logarithm problem almost when I was in your shoes because they didn't have a log button on my calculator. Certainly, and not even a log base button on my calculator to make matters worse. If I just had regular log on my calculator, I could just do the formula real quick. But here I have to look them up back in the textbook. The same was true for like, normal PDFs and CDFs, and if you've had stat. Anybody had stat? No. Okay. Never mind that. Anyway, blah 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 blah. It's the same thing we're talking about here. Just use the log base, right? So if I want to do this using the change base formula, I could write log of 16 divided by log of 3. Or I could do natural log of 16 divided by natural log of 3. Why would I typically choose one of those two logs to use as my base in my log base formula? They're buttons on my calculator, right? Or they were the values in the back of the textbook back when I had to look them up. Right. Or in your guys' shoe, what do? Log base button, and then type it in exactly like it looks on your calculator. If you don't remember where the log base button is, it's under the math menu, and it's down towards the bottom. I think it's like Command 0 or something. It's deep down there. You have to scroll a little bit. Not all fresh on the exact location of it on the menu anymore because it's that's the first week of school. I haven't even really pulled out a calculator to try to do anything with it yet. Okay. And notice I round my answer here to 3 sig figs because it's not an exact value. What about log base 6 of 10? Same idea. Natural log 10 divided by natural log 6, or you could do common log 10 over common log 6. Either is fine. Type that in your calculator. Round to 3 sig figs. Boom. is it appropriate to just type up or to write down the whole decimal, 1.285097209? No, why not?
It's not 3 significants.
Well, that is a rounded answer, right? Just because it filled up the entire display in your calculator doesn't mean that's the exact value. That's an irrational number that has gone on forever. Your calculator's memory has 99 decimals stored. It's only going to display those first 9 or 10 or whatever. That is a rounded answer. If you're going to give a rounded answer, it needs to be rounded to 3 significants. So just because you copied the whole calculator display doesn't mean that you didn't round. The calculator might have rounded on you, and you might not have realized it. Okay. Everybody's good? Okay. I just want to point that out because sometimes that's like, I just wrote down the whole calculator display. Why is that not exact? Well, it's an irrational number. You know, most logarithms are probably going to be irrational numbers. It's very uncommon to get a logarithm that's a rational value. But that's it for today. What do you guys think? I don't want to play sport because, quite frankly, I don't have the class working it out to like jump up a day. I would say that you guys should take this remaining 40 minutes, grab a textbook, and start on that 23 through 20 or page 23, 1 through 20. Start cranking out that homework assignment.
We've already worked so hard.
I know, I'm ready to Friday.
I don't think so.
I thought you were ready.
What are the
Page 23, number 1 through 20. Grab a textbook off the thingy machine.
I can't teach you.
It's got
Handing them out.
I have a group over here.